This equipment case has a mass of 10.0 kilograms on Earth. Take it to the moon, what changes? Its mass, its weight, both, or neither? Everyday English often uses mass and weight as if they mean the same thing. In physics, they describe different quantities. Mass is a scalar quantity measured in kilograms. It is a measure of inertia, how difficult it is to change an object's velocity. Give this case the same resultant force in either location, and its acceleration is exactly the same, because its mass has not changed. Weight, however, is different. It is the gravitational force acting on the case. Weight is a vector measured in newtons, and it points along the local gravitational field. Near Earth or the moon, weight points towards the centre of that body. So its mass and inertia stay the same. The local field changes, so its weight changes, and that makes the case easier to support on the moon. The magnitude of the weight is W equals mg. Here, m is the mass and g is the gravitational field strength. Near Earth's surface, g is 9.81 newtons per kilogram. That means each kilogram experiences 9.81 newtons of gravitational force. For this case, W equals 10.0 multiplied by 9.81, giving 98.1 newtons downwards. But at the moon's surface, G is only 1.62 newtons per kilogram. The calculation becomes 10.0 multiplied by 1.62, so the weight is 16.2 newtons. Its mass is still 10.0 kilograms, however. The answer to the opening question is therefore, mass stays the same, weight changes with G. The unit newtons per kilogram tells us that G is a gravitational force per unit mass. For this case, G equals W divided by m. A newton per kilogram is equivalent to a meter per second squared, because 1 newton is 1 kilogram meter per second squared. When gravity is the only significant force, a free-falling object's acceleration has the same numerical value and the same direction as the local gravitational field. Learn W equals mg. It's not printed in the AQA, OCRA or Cambridge formula booklets. EdXL does provide it, but it's such a useful formula that it's worth memorising anyway. Ideal beam balance compares the case with known masses. Both sides are in the same gravitational field, so the case balances against the same known masses on Earth and on the Moon. A Newton meter uses the extension of its spring to measure tension. For a stationary hanging case, tension balances weight, so it reads 98.1 newtons on Earth and 16.2 newtons on the Moon. If the case accelerates, tension need not equal the weight. Now, if we let the case and force plate fall together near the Earth, if you ignore air resistance, gravity is still acting, so the gravitational force on the case remains 98.1 newtons downwards, but the plate is no longer pushing upwards. The support force and its reading are 0. This apparent weightlessness is not the absence of gravity. Astronauts in orbit float relative to their spacecraft because both are in continuous freefall around the Earth, not because gravity is so small. In an exam, keep the two quantities separate. If the same object changes location, its mass is unchanged. Use the local value of G in W equals mg. Report the weight in newtons and give its direction when needed. In this freefall scenario, a 0 scale reading means 0 support force, not 0 weight. Next, we will keep the case falling, add air resistance, and see how terminal speed is reached when the drag balances weight.